My name is Gary Harris. I want to welcome you all to the 97 International Space Development Conference. And our first speaker is a fellow named Steve and Howe. And Dr. Howe is from my old alma mater, Kent State University. And I heard him speak yesterday. He's an excellent speaker. I enjoyed it. And he has a long list of information in his biography. Let me just sum it up to say that he really is a nuclear rocket scientist. So without further, I'll introduce you. Thank you, Jerry.
Good afternoon. Good afternoon. Welcome you all here to what I hope is a little bit more unusual, a little bit more speculative presentation. I've retitled it slightly to making a profit from the lunar base or selling refrigerators to the Eskimos. And that what I'd like to discuss today is perhaps a slightly new perspective and some new technologies that I think might enable a private lunar base, an actual commercial venture to be put on the moon in the near term. And that's why I kind of changed it from setting a vacuum salesman title to selling refrigerators, in that I believe most people who've looked at this in the past have said the biggest single obstacle to a private lunar base is the launch costs. It costs too much to put things in orbit. And that certainly is a viable approach. Alternatively, from a business standpoint, it's really not the launch cost per se, it is the ratio of your income to expenses. So if you can reduce operating costs and increase your income, then you can still make a profit, and you really don't care what the launch costs are. So I'm all supportive for the X-33 and the RLPs and all the launch programs that are going on, a great deal of effort's going into that. But I thought I'd take a stab at looking at how might you really exist in a private venture on the moon, and there's some new ways of doing it and a new way of looking at it. This is an artist concept from a thing called the National Commission on Space report down in 1985, and it's a wonderful visionary look of everybody, nice shirt-sleeve environment, growing plants and all kinds of things on the ground, windows looking out on the lunar vista. The problem, of course, is there's a rather intense radiation field out here that's now streaming in. And it may allow you to grow giant oranges, perhaps, but it's probably not a very healthy environment to live in. So as the engineering community started to take a hold of that concept, they came up with this, which is less motivating and inspiring, perhaps, but a little more practical. And that is that you have these nice little trailers covered in lunar soil to protect you from the space radiation, but this doesn't look very, very pretty. But still, it's starting to recognize the problems inherent in living on the moon. Then we get to one other artist concept, as engineers get a little more excited about the idea, and now we're mining oxygen. We have an oxygen miner, big, heavy front-end loaders, treaded vehicles, tons of material being processed, making all kinds of lunar oxygen for the return of the ship back to the Earth. So we're starting to get a little more grandiose in thinking. The problem with this kind of thinking is, how does the engineer sitting in his cubicle back here on the Earth between lunch breaks know that this treaded vehicle is going to work? How does he know that the dust doesn't get into the gears and the seals and the bearings and this thing lasts about a day? How does he know in a 1/6 G that the tread level isn't going to just sit there and spin in the loose dust? And so the point that I have tried to push for a long time is that he doesn't know. You cannot pre-design the equipment to go up into the lunar base. You really have to let the people that are on the surface build the things they need. So that's kind of my two-point philosophy. That is, there's two things you need to survive a lunar base. One is a power-rich environment. You need to provide more electrical power than you think you might ever need. And the reason that I push this very strongly is that you just that same point you don't know what you're going to need on the surface. You've really got to have the ability to manufacture it. You've got to be able to cut steel, weld steel, electrolyze water, turn the soil into glass or lava to produce the things that you end up needing. It allows you also then to survive the crisis. Any kind of expansion and adventure like this, you're not going to foresee all the problems. So the first thing is make a lot of power, more than you think you will, because you'll, in a Malthusian way, you will expand to absorb whatever you've got. The second thing is take the tools, not the thing. Don't take the front end loader, don't take the little buggy. Take the tools that allow you to make the bearings, the frame, the power plant, that allow you to build what you decide you want once you're there. So those are kind of my two basic philosophies, if you will. And this is a nice NASA artist concept that I use to kind of epitomize this. You know, we got a equivalent of a flat tire on the lunar surface, and you have to kind of take it off and replace the ceramic bearing with one that you made. The point, another point to this is that you don't want a warehouse full of spare parts. Things are going to wear out, things are going to break, and I don't want to have to lift tons of material that I may or may not need depending upon how much we use it. You want to be able to manufacture it when you need it, replace it, and get on with the work. Now the question is, can you really kind of do these kind of nice concepts with large telescopes arrays that you're going to run around with the nice buggies if you're going to try to make it on the surface? So the question is, what technologies might you use? So here I have a rather long list of what I think are some key technologies pertinent to the lunar base. And I'll just run through it quick and then I'll try to expand on each one. Nuclear power, submarine, water shielding, microwaves, sulfur, and ELF. Power. Let me harp on the power just a moment. And this is a nice chart. I think it's circa 1989. Came out of JSC, showing a comparative study between different power supplies that you can generate. Mission duration down on the bottom here, 10 to the 4th-ish. Right in here being about 1 year time frame. And this right just below 10,000. And then power, electrical power in kilowatts on the ordinate. So if you're looking at the space station, which is now down to I think 50 kilowatts, or perhaps maybe up to 75, you could potentially do a solar dynamic system with some nice reflectors on the lunar surface and have a power plant. But if you really get into how much that weighs and essentially cost is mass, then you really, and you want to go up to the megawatt level, you really got to go into nuclear type systems. And so this is kind of the conclusion I reached very early on. If you're wanting to be power poor, you can live with the solar dynamic and try to manufacture it on the surface. But the easiest way is to bite the bullet in the beginning and say, I need a nuclear reactor. Now in this country, they may not be so easy, but there are other countries where nuclear power isn't quite so treated in such a paranoid fashion, and reactors are relatively straightforward to develop. This is an artist concept, an old program that was called SP-100. This was the U.S. space power program that died in the 92 and 93 time frame. And I just wanted to show you the little red blob here. That's the reactor. The rest is the radiator. This has to get rid of the waste heat because the efficiency of conversion is about 10% from thermal power to electrical power in the reactor. That means you've got to get 90% of the heat off into space. And that's what this whole massive radiator is for. And just to elaborate on the schematic, same kind of deal. The power generating part is this little trash can sized blob here. The rest is to get rid of the waste and to get it off into space. And I want to come back to this a little bit later then as to why that may be important. And just to set the scale, 60 centimeters by 75 centimeters. So it truly is a trash can sized operation. Here then is an artist, again, envisionment, if you will, of how this might be deployed. And there's a couple of points here that I'll come back to later, but essentially you land, you sink a small hole, you set an explosive charge, you blow out a lot of regolith, and then you can essentially drop your reactor down in with the same type of space radiator that radiates then the waste heat off into the vacuum of space. But again, this is kind of the big massive part, and I think there's a way we can get rid of this. And if you take off the radiator and have some other way of getting rid of the waste heat using the local resources, this becomes a very small, compact operation. I'll get to that momentarily. First, I want to break to subterrane. Subterrane is a rather simple concept that was again developed in the 60s at Los Alamos as a way of drilling very, very deep wells. And it was developed supposedly to do the 10,000, 15,000 foot kind of wells for oil exploration. And it was essentially simple. You take a molybdenum tip, it's shaped kind of like a top, you heat it up to really hot temperatures, and it melts its way into the ground. And surprisingly, it was very successful. It would melt at about a meter per hour kind of number. Here's a nice little picture showing the hot molybdenum, and it just kind of sinks down. The difficulty, the reason it never got developed commercially, is it has a little problem of wandering. You can't really control it and make a nice straight shaft. So as far as oil well exploration, it was not a viable concept. But if you want to drill a hole on the moon, it looks very attractive. If you recall some of the stories that came out, and I believe it was Jack Schmidt that had a big problem drilling on the surface. The problem with drilling on the moon is you don't use any fluids. You don't bring up the grit and the stuff you've dug out of the hole, so it stays down in there. Pretty soon the bit locks up, and as we saw in some of the past historical pictures, the astronaut is kicked sideways and thrown on his back. So drilling on the surface of the moon in a dry environment is very difficult. Whereas this technique allows you to essentially sink a hole as long as you have power. You can, and it gives you a nice little glass lining. It's a very high density, essentially lava-lined hole, but it's a very nice and clean hole. So this is kind of in the tuff that we have out in Los Alamos, a borehole. They developed a number of different power probes, different geometries, going all the way from just the one we just saw to various coring techniques where you could actually take out a non-heated, non-perturbed section in a core from the material. So you can, again, as long as you're power rich, this is a nice way of drilling into a dry environment and is useful for the moon. Now, one of the innovative things they did, they walked up to a pile of rubble. I mean, it was just various sized rock and sand and things. You took the subterrane probe, drilled in horizontally, and each one of these little holes actually fused together, if you did it right, and you made a nice little storm cellar here, and then you dug out the rubble, and you've got yourself at least a cellar of some kind, at least a storage shape that you could put an inflatable in or something like this. It gave you a structural element. And that was one of the applications then that we felt was pertinent to the lunar soil, which is very loose, but can be consolidated then in this kind of an arrangement. So this was a paper that came out from the Base Conference in the mid-'80s using the subterrane to make at least a storable area. So that's one technology. Again, all I need is power. The second one, I'm trying to get through this quickly, I know I'm running out of time. Water shielding. As I talked yesterday, the galactic cosmic rays are a big problem in space exploration. You're getting essentially half your lifetime dose per year, well, a quarter of your lifetime dose per year from galactic cosmic rays. You've got to shield yourself. Now this can take up to about 9 feet of lunar soil if you want to really cover yourself up. Or you can cover yourself with water. Now water is very nice from a number of different perspectives. It's a very good shield against the radiation. It doesn't produce very many secondaries, and it stops all the charged particles from coming in. If you make it in between two hulls, you make double-hulled habitat with water in between, then if it gets punctured by a micrometeorite, then the water that escapes tends to freeze in the vacuum, and just like the shuttle toilet sickles they always have problems with, it's self-sealing. So it doesn't all leak out. Essentially, you stop the micrometeorite and you seal up until you come out and roll over the hole. A big, big advantage of this, in my opinion, this double-hulled habitat idea, is that you have a problem with waste heat. And that is body heat, heat from electronics and instruments is a very low-grade heat. It's hard to get rid of. It's not high temperature. And so the shuttle has, of course, the big payload bay doors to do that. A very large area to get rid of a very low amount of heat. But if you have this double-hulled habitat, I believe that you'll have essentially a boundary in the water where the low-grade heat keeps some inner layer fluid, and that level, that boundary actually adjusts depending upon how much heat you're generating in the habitat. But it's intrinsic, it's correcting. There's no active pumping. It just, if you generate a lot of heat because you're exercising, that boundary layer moves out toward the wall, and if you're sleeping, then it'll move in. But it's a low-grade heat absorber. Of course, it's a source of hydrogen and oxygen. If you have the unforeseen crisis, I can now electrolyze it with my extra power, making hydrogen and oxygen to live off, and it's nice to have a shower now and then. And so a hot shower, a lot of extra water is almost as valuable as a lot of extra power. One of the other technologies, moving on then, and I'm sorry I don't have more view graphs on this particular topic. This is essentially making glass out of lunar soil using a standard microwaves. This is 2.45 gigahertz, just like a microwave oven. And what we actually did here is a little bit unfortunate. We had actual samples from the different Apollo missions. Apollo 11 was this sample. We had created some very accurate simulants of the lunar soil and microwaved them into a glass form. Measured how much time it took and how much the coupling was. Turned out when you took a real sample and put it in, it melted a factor of 3 faster, 3 times less time, if you will. So we were caught by surprise in the manufacturing of this and actually melted it, which is not what we had necessarily intended to do. But the good thing of this is that the lunar soil readily couples to microwaves, and the idea then is that it's quite simple to make lunar glass roads, lunar glass building blocks. You don't have to necessarily pre-sift the soil, it consolidates well, and that this is a very good structural material for the use on the moon. If you do pre-sift it, part of the idea is that you can make it translucent so that if you covered your habitat with that much glass to stop the cosmic rays, it will still let sunlight diffuse through so you can have your greenhouse. So you can have a nice radiation-free environment that still is illuminated and you can grow your plants. One other aspect that was looked at is if you can microwave this glass in a very, very dry environment, you can actually produce glasses with a tensile strength near steel. That the weakness of glass usually comes around from water molecules getting in the fabrication when they join, and that weakens the tensile strength of the glass. And so we had a high-strength material, translucent material, or just a road building material out of the microwave process. And of course, this made us envision, the crystal sitting on the moon. That's a little bit grandiose, but you've got nice glass roads, glass-covered habitats, high-strength glass cable for your telescopes. So it's a nice envision, but this may be an excellent structural material. Very quickly, sulfur. There's about 1/10 the amount of sulfur as there is oxygen if you process lunar soil. Sulfur's got some really nice applications. Here's a whole list of them. One of them is as a propellant, in that sulfur combines with oxygen very nicely to make sulfur dioxide, which condenses out on the lunar surface and then increase the gaseous atmosphere of the region. So it's a rocket fuel. The other one, I think, is if you blend the sulfur back into the soil, you have a nice heat sink for the reactor that I talked about earlier. You improve the thermal conductivity of the soil. I now don't need that big radiator. I can essentially bring the waste heat into the dirt itself, and using the soil as a conducting medium, take that waste heat into the dirt. And so I think as a thermal heat sink down here. But here's a whole list of potential sulfur applications. The last thing I want to just get to very rapidly is called directed light fabrication. Maybe I'll show this one. This is a method being worked on back in the laboratory. You take a 5 or 6 axis machine with a controlled laser beam. You inject metal powder at the focus of that beam and lay down a layer of actual metallic material so you can create from a computer model 3-dimensional objects. So we can start essentially, I can upload the shape of the object you may need, and you can manufacture it on the spot. These are made out of tungsten right here, which is a pretty high melting temperature material. We've done aluminum, nickel, we've done steel, tungsten, molybdenum. It's pretty much metal independent, but you can make then a 3-dimensional complex shape. Those are the technologies. If I can quickly get to what you might sell. So that's how I think you've reduced operating costs, is by using these technologies to live off the land in a roughly simpler manner. Now, what might you sell? Very quickly from a lunar operation. First thing, of course, is rocks. I mean, the scientific community will buy rocks for a while until they get so plentiful that they're no valuable. Souvenirs, might go pick up some of the stuff from the Apollo sites, sell back some things that that were left by Aldrin and Armstrong. The really controversial thing that I'm advocating is that, is it any more realistic to be able to copyright a song where you get paid royalties every time someone uses it and not copyright scientific data? If I go up as a company and build a distributed optical telescope that can see Earth-type planets and have that information, can I change the laws of the country and copyright that so that every time someone references that in a professional manner, they have to pay a royalty? And the reason this would be nice from a lunar standpoint is that the dollars per kilogram for information is really high. Information doesn't cost a lot. And if I can get scientific data in a copyrightable manner, then I have something I can export from the moon and make money off of. And other things you might do besides the astronomy, which will really give you a unique position, you can start to do things like genetic engineering and propulsion that might be hazardous to the biosphere, have political obstacles on the ground, but that you could do up there. But again, can you now sell that information and make money off of it? Advertising. It'd be nice to show someone in front of the Apollo 11 site saying choice of the next generation. That might work. Raw material. Here's the real key, I think. Once humanity gets up into low Earth orbit, starts having hotels and a tourist industry, at least a lot of the studies I've seen show that the shielding material and the structural material to build those hotels, it's cheaper to go to Leo from the moon than from Earth to Leo. So suddenly I have a need for this material. That justifies the lunar base. Now we have results from a 1985 study that said if you've got a lunar base, it's cheaper to get water to the moon from Phobos than to the Earth, to the moon from the Earth. So suddenly everything kind of starts to click, and you really just need this first step, this first tourism in orbit to make that economic justification take place. One other aspect that I think you can sell is archiving data and materials. Everything lasts on the moon for millions of years. You can sell genealogical records, you can sell statues, whatever you think people may pay to have something stored for infinity. And so I think just an archiving place. So in essence, my point, I guess, although I rushed through it quickly, is that I believe you can sell refrigerators to Eskimos if they have electricity and they have a need for a controlled environment they can't get any other way. That you can made by lunar-based products if you provide unique information, services, or goods. The trick, of course, is convincing the market that they really need that kind of stuff. So I believe there are things to sell. I believe you can make operations cost down, and I'll try to get out of here and leave you with just one little tidbit. I do have a personal web page where I talk about these concepts in a little more detail and have links to electronic versions of the technical papers on the technologies. And I'm going to do a shameless plug. I've written a science fiction adventure novel that incorporates essentially most of what you've seen in a nice adventure story, which is available off of this page, or I have a few copies with me. So thank you. Happy to take some questions if there are.
We'll leave some time for some questions at that.
Oh, you going now?
Maybe a quick.
I was going to ask, why lunar stuff as opposed to asteroids and Venus?
Delta V. It's just cheaper to get to the moon. It's stable platform. You don't have to do a lot of rendezvousing. You don't change position. It's just a lot cheaper to go back and forth to the moon than to try to grab an asteroid.
Well, I'm not talking about a main belt asteroid.
But you're going to catch it and bring it here, or are you going to do a rendezvous on it and then ride it?
Yeah, right.
I mean, it's just Delta V. I mean, it's just rocket time. It's fuel propellant. I think it's cheaper to get to the moon first, in my opinion.
How do you heat the penetrator?
Electrically. There's just pure electrical resistivity.
Would you put your email address back up?
Sure. I know that was an extremely fire-hosed presentation. Anybody else? Well, thank you.